A case study on speech recognition using DSP processor. Speech processing is the study of speech signals and the processing methods of these signals. It is necessary for speech recognition. The signals are usually processed in a digital representation, so speech processing can be regarded as a special case of digital signal processing, applied to the speech signal. Speech recognition. Speech processing can be divided into the following categories. Speech recognition, which deals with the analysis of the linguistic content of a speech signal. Speaker recognition, where the aim is to recognize the identity of the speaker. Speech synthesis, the artificial synthesis of speech, which usually means computer-generated speech. Here we are discussing the implementation of speaker recognition system on DSP processor TMS320C6713. Overview. Speaker recognition is the process of automatically recognizing who is speaking on the basis of individual information included in speech waves. This technique makes it possible to use the speaker's voice to verify their identity and control access to services such as voice dialing, banking by telephone, information services, voicemail, security control for confidential information areas, and remote access to computers. For example, users have to speak a PIN, personal identification number, in order to gain access to the laboratory door, or users have to speak their credit card number over the telephone line to verify their identity. By checking the voice characteristics of the input utterance, using an automatic speaker recognition system similar to the one that we will describe, the system is able to add an extra level of security. Principles of speaker recognition. Speaker recognition can be classified into identification and verification. Speaker identification is the process of determining which registered speaker provides a given utterance. Speaker verification, on the other hand, is the process of accepting or rejecting the identity claim of a speaker. Figure 1 shows the basic structures of speaker identification and verification systems. Feature extraction and feature matching. Feature extraction is the process that extracts a small amount of data from the voice signal that can later be used to represent each speaker. Feature matching involves the actual procedure to identify the unknown speaker by comparing extracted features from his/her voice input with the ones from a set of known speakers. We will discuss each module in detail in later sections. Speaker identification. Speaker verification. All speaker recognition systems have to serve two distinguished phases. The first one is referred to the enrollment or training phase, while the second one is referred to as the operational or testing phase. In the training phase, each registered speaker has to provide samples of their speech so that the system can build or train a reference model for that speaker. In the case of speaker verification systems, in addition, a speaker-specific threshold is also computed from the training samples. In the testing phase, the input speech is matched with stored reference model, S, and a recognition decision is made. The part which is given above it is brief about speech recognition. If you feel, you can skip and concentrate on the part given below. Speech recognition using DSP processor. Speech feature extraction in speech recognition. Introduction. The purpose of this module is to convert the speech waveform, using digital signal processing, DSP, tools, to a set of features, at a considerably lower information rate, for further analysis. The speech signal is a slowly timed varying signal. It is called quasi-stationary. An example of the speech signal is shown in Figure 2. When examined over a sufficiently short period of time, between 5 and 100 millisecond, its characteristics are fairly stationary. However, over long periods of time, on the order of 1/5 seconds or more, the signal characteristic change to reflect the different speech sounds being spoken. Therefore, short-time spectral analysis is the most common way to characterize the speech signal in speech recognition. Speech signal. A wide range of possibilities exists for parametrically representing the speech signal for the speaker recognition task, such as linear prediction coding, LPC, Mel frequency Cepstrum coefficients, MFCC, and others. MFCC is perhaps the best known and most popular and will be described in this paper. MFCCs are based on the known variation of the human ear's critical bandwidths with frequency. Filters spaced linearly at low frequencies and logarithmically at high frequencies have been used to capture the phonetically important characteristics of speech recognition. This is expressed in the Mel frequency scale, which is a linear frequency spacing below 1000 Hz and a logarithmic spacing above 1000 Hz. Mel frequency spectrum coefficients processor. A block diagram of the structure of an MFCC processor is given in Figure 3. The speech input is typically recorded at a sampling rate above 10,000 Hz. This sampling frequency was chosen to minimize the effects of aliasing in the analog-to-digital conversion. These sampled signals can capture all frequencies up to 5 kHz, which cover most energy of sounds that are generated by humans. As been discussed previously, the main purpose of the MFCC processor is to mimic the behavior of the human ears. In addition, rather than the speech waveforms themselves, MFFCs are shown to be less susceptible to mentioned variations. Block diagram of MFCC processor. Frame blocking. Windowing. The next step in the processing of speech recognition is to window each individual frame so as to minimize the signal discontinuities at the beginning and end of each frame. The concept here is to minimize the spectral distortion by using the window to taper the signal to 0 at the beginning and end of each frame. If we define the window as where n is the number of samples in each frame, then the result of windowing is the signal. Equation. Typically the Hamming window is used for speech recognition, which has the form SO_divider. Also read. Case study of interpolation and decimation. How to configure and run DSP processor. Case study on barrel shifter, digital signal. Linear convolution program using MATLAB. SO_divider. Fast Fourier transform, FFT. The next processing step for speech recognition is the fast Fourier transform, which converts each frame of n samples from the time domain into the frequency domain. The FFT is a fast algorithm to implement the discrete Fourier transform, DFT, which is defined on the set of n samples xn, as follow. Mel frequency wrapping as mentioned above for speech recognition. Psychophysical studies have shown that human perception of the frequency contents of sounds for speech signals does not follow a linear scale. Thus for each tone with an actual frequency, f, measured in Hz, a subjective pitch is measured on a scale called the Mel scale. The Mel frequency scale is a linear frequency spacing below 1000 Hz and a logarithmic spacing above 1000 Hz. Speech recognition. Mel spacing. One approach to simulating the subjective spectrum is to use a filter bank, spaced uniformly on the Mel scale, see Figure 4. That filter bank has a triangular bandpass frequency response, and the spacing, as well as the bandwidth, is determined by a constant Mel frequency interval. The number of Mel spectrum coefficients, k, is typically chosen as 20. This filter bank is applied in the frequency domain. Thus it simply amounts to applying the triangle shape windows as in Figure 4 to the spectrum. A useful way of thinking about this Mel wrapping filter bank is to view each filter as a histogram bin, where bins have overlap, in the frequency domain for speech recognition. Spectrum. In speech recognition this is the final step, we convert the log Mel spectrum back to time. The result is called the Mel frequency spectrum coefficients, MFCC. The spectral representation of the speech spectrum provides a good representation of the local spectral properties of the signal for the given frame analysis. Because the Mel spectrum coefficients, and so their logarithm, are real numbers, we can convert them to the time domain using the discrete cosine transform, DCT. Therefore if we denote those Mel power spectrum coefficients that are the result of the last step are. Note that we exclude the first component, 0C from the DCT since it represents the mean value of the input signal, which carried little speaker-specific information. This was the case study on speech recognition using DSP processor.